what we heard from our speakers, I think, again, you have to break the market into today and tomorrow. Today, what Intel and NVIDIA and AMD faced was that they were undertaking something that was physically impossible, and they had to make it possible. So there's been a whole lot of rocket science going on there. Going forward to that third-party open chiplet market, I think we've got a few very fundamental challenges that are still not overcome entirely. One is standards for interconnect between the chiplets. We have UCIe and a few other proposals that define the physical layer, but they don't define enough layers of the protocol stack to guarantee that any two chiplets will be interoperable. Chiplet-based multi-die systems are taking the industry by storm. Are you ready for new and unfamiliar challenges around die-to-die connectivity, chiplet integration, and system reliability? Synopsys, backed by its broad experience, close ecosystem collaborations, and comprehensive IP and EDA solution, offers help for fast chiplet-based multi-die system development. Visit synopsys.com/multi-die.
This is the wrap-up session of the 5 episodes we've run on the Dig Deeper Chiplet videocast. And we decided to get together at the end so that we can all compare notes, what we learned, what we still haven't figured out. There are a lot of things we haven't figured out yet. But I'd like to introduce Ron Wilson, who has been the host of this series. Hi, Ron. And Bolaji Ojo. He is the co-founder of the Ojo-Yoshida Report. He has been a vicarious bystander of this chiplet series, but he has some questions. So 3 of us are here to talk about what we have learned. And, I just want to go back to the very basic. What is a chiplet? Let's define a chiplet. I think we heard a little bit different definitions. Can we go over this a little bit, Ron?
Sure. I think the first one we heard, and probably the first one most people think of, is a chiplet is any piece of silicon that's been put into a multi-die assembly. But a couple of our speakers during the series wanted to refine that a bit. And I think the best refinement we got was that maybe not today, but in the future, a chiplet is going to be a die that has been designed specifically for use in a multi-die assembly. That will turn out to be a big difference from just anything you slap onto a substrate. And I think as the discussion progresses here, we'll see some of the reasons for that distinction.
Yeah, that distinction is an interesting one because it didn't really, I'm such an amateur here. It didn't really occur to me really the difference of the chip used in SoC and chiplet in the chiplet, right? And the chiplet is something, I think it was defined by one of the speakers, that the chiplet is not soft IP. It's hardened, so you can't modify it. While SoC, when you have a chip, it is essentially, it's more malleable. People can tell the chip makers, can you modify this to do that? That sort of thing. That difference did not occur to me until I had listened to this series. What's your view on this, Ron?
I think the IP analogy is a really good one. It may not be obvious to people who aren't working in the chip design business, but the way you design an SoC these days is not sitting down and starting to write out logic. SoCs are assembled out of intellectual property that's already been designed and tested by somebody else. And SoC design is really more of an assembly and test process than it's a design process. The only time anybody actually writes RTL code is if there is a function that they can't find anywhere else. It's a last-ditch thing. And in a way, chiplets are very analogous to IP in that building a multi-die assembly is a process of assembling individual little functional blocks. And it has a lot of the same problems that SoC design does, in that you have to find a block that does the right thing. You have to figure out what the interfaces are and get them to match up. And then you have to assemble them in a way that performs the function you really want. But as you point out, Junko, the overpowering difference is in the real world, most IP gets modified before it's actually incorporated into the SoC design, because that's just a matter of changing some code somewhere. And you talk the vendor into doing it under the threat of going back to ARM and getting theirs instead.
Right.
So there's a lot of flexibility there.
Yeah.
If you're assembling chiplets designed and manufactured by other people, they're already silicon. There isn't any easy way to modify them.
Right.
Now, there may emerge a backdoor solution to that, but we can talk about it in another context.
May I jump in here? As a bystander, just listening to some of the discussions that you've had with our guests, one of the things that struck me was the history of chiplets. It seemed to be like, it was all over the place. People claiming that, they were the original thought leaders in coming up with chiplets and things like that. I wonder, both of you, if you can just go back based on what our guests have talked about, what really is the root of chiplets, and who can we really say, okay, you know what, this idea belonged to this person, or maybe it just belonged to everybody?
I guess the original root depends on how deep you want to dig. There were people doing multi-chip assemblies on very small substrates as early as the 1980s and 90s. The aerospace industry was doing this to desperately try to cram the electronics they needed into a serviceable module back during the Vietnam War era even. Those weren't chiplets because they were prepackaged ICs, but people were mounting multiple dice on a substrate and putting it into a package back in the days when IBM was still building computers. So the roots of multi-die modules go back a long, long ways, the 90s at least. The idea of chiplets in the sense of an open market for interchangeable parts like IP is a more recent phenomenon, but it's still an old one. The Defense Department was talking about that in the 20-teens. They were urging people to develop it because it was the only way they saw of going forward while controlling contract costs. So it's very old.
Yeah.
And like most great ideas, it still isn't here.
Yeah. No, but the motivation, that comes to my next question. The motivation, the roots of the motivation is similar in a way, that people are looking for cheaper, the lower cost to assemble eventually the chip that they need, right?
Mm-hmm.
So let's talk about is it cost the only factor? What have we heard during our series, that what motivates people to go for chiplets?
I think at this stage, where chiplets are primarily being done in just a few very wealthy places, the primary motivation is what the industry would call the reticle size limit. People building CPUs and GPUs are trying to design chips that are simply too big to be manufactured because of constraints in the way that the images are printed onto the wafer. And the only way around that is to break the design up into multiple pieces and build them on separate dies. And right now, that's the primary motivation. It's not clear at this immature stage in the technology that it's cheaper, but it's physically possible. Where, for instance, building Intel's GPU with 47 separate dies on it would not be physically possible on a single die.
Right.
But once Once the industry starts maturing, I think cost will become a significant issue because the cost of a die just doesn't go up linearly with the area. It tends to go up exponentially with the area for a number of reasons, including yield.
Yeah.
Also, just I think access to the technology becomes an issue. To get a huge amount of stuff onto a given die area, you have to use a very, very advanced process. Those processes are disastrously expensive if you're not building things in very high volume. And because of trade barriers and just practicality, they're not available to everyone. If you have all the permission in the world and you go to TSMC and say, I want this monster chip in 3 nanometer and I need a dozen of them, they're going to take you to coffee and send you home. So there are a number of barriers to building a very, very large die that chiplets can circumvent.
So, Ron, just wondering if our guest gave you an idea of where the technology is at now in terms of everything that you've described now, where we are in its evolution.
I think one of our speakers said we are at the stage of crawling but not yet walking, to use the old walk, crawl, run analogy. There certainly are systems in package on the market today that are assembled from chiplets in a loose definition of chiplets. Generally, they consist of a huge processing die surrounded by stacks of high bandwidth memory dies with a couple of peripheral interface dies. So it's a very, very simple partitioning and no attempt to break the real core of the system into individual dies. But those are still ambitious, and they're the pipe cleaners, if you will, that are being run through the supply chain to gradually get things working so that more ambitious designs can be done.
The thing that actually originally the way that I got interested in chiplets is because there are players who are not necessarily the traditional chip players. I'm not talking about AMD, Intel, Nvidia. Those guys have been paying attention to what's going on in semiconductor, technology for a long time. But now we have new players like automotive companies, system companies that have never been in the chip business before. Now they're suddenly kind of waking up. What if we use chiplets? What could we do? Right? I mean, that is kind of open, open up the whole idea of chiplets in my mind. Am I wrong about that?
No, I think you're exactly right. And those are the people who are starting to run into fundamental limitations. I think our speaker from IMEC said it very clearly. When he talks to people in the automotive industry, they talk about needing to put a data center in a car to achieve the kind of automation that people are expecting them to accomplish. But there is no way they can do that with the kind of development budgets that they have available and the kind of volumes that they can produce. I mean, if you look at it in the context of cell phones and data center server boards, cars are kind of a low volume market. That's
Right.
I think any auto manufacturer would be delighted to make as many cars as there are CPUs in one data center.
Yeah.
Very true. Very true.
So the automotive people, the aerospace people, see themselves running up against this hard limitation where financial viability stops well before computational needs are satisfied. And they see chiplets as a way to tunnel through that barrier.
On that basis, again, Ron, I wonder, at this time of the evolution of the market for chiplets, are you seeing, or did our guests talk about potential winners or the leaders in that market at this moment, and what it will take for them to retain their leadership or to gain additional market share?
I think we have to look at that question in two pieces. One, as Junko referred to a few minutes ago, there are the Intel, AMD, NVIDIA people who are basically vertically integrated multi-die assembly manufacturers doing virtually all of their own silicon except for the high bandwidth memory. And in that segment, I think they are the leaders and they will continue to be for the foreseeable future. Most of our speakers seem to agree that the other segment, automotive, for instance, hasn't really emerged yet. And so we don't know who the leaders will be there. And because that hasn't emerged, there is nothing close to a third-party market for chiplets where you could buy them off the shelf the way you can buy IP today. So way too early to call it there. I think the one thing we did hear from all of the speakers is that they believe that is coming. They differed a little bit on whether it's coming in a few years or coming within the decade. But everyone was pretty confident that it was technically feasible and financially necessary.
No, that's a good point. I think that brings to my next question that I had in mind is that it was explained to me that chiplet market today, there are like three buckets. One is a single vendor environment, just like Ron just explained, Intel, AMD, NVIDIA of the world. It's sort of vertically integrated. It's single vendor environment. Another is the multi-vendor environment. I think this is beginning to happen. We haven't totally finished this job yet, but it's a multi-vendor environment. And the third one, which is the one Ron always asked, every guest we had, Ron always asked, do you think it's possible to have an open chiplet market? This is the question that Ron always asked, right? So tell me Ron, tell me about this evolution of the different sort of buckets that the chiplet, landscape is today.
Well, certainly it all started out with Intel and a couple of other companies working on the chiplet idea because the DoD was handing out contract money for it. And that was really the beginning, not only of turning the chiplet idea into reality, but also of formulating the standards that would be necessary to make it a reality. And so those companies both had the need and the technological leg up to apply the chiplet idea to their own GPUs and CPUs. So that was the first generation. And I think they will continue to satisfy their own needs using multi-die assemblies. Whether they ever start using third-party dies other than memory dies, I think is an open question.
Yeah.
Intel, AMD, NVIDIA are not big champions of using other people's IP other than ARM.
Yeah. That's a good point. Yeah.
Which, of course, raises another tantalizing question of, will ARM eventually become a chiplet vendor? But I won't go there.
That's another session. Yeah.
Yes. The next step, I think, as we've been discussing, is that there are very pressing needs that are going to push some application areas like aerospace and automotive into chiplets, whether the infrastructure is ready or not. And I think a lot of our speakers in this season said that's already happening. It hasn't produced any productized assemblies yet, but the work has already started. And that's had two external effects. One is it's starting to gel a supply chain that can support more than just Intel, AMD, and NVIDIA. And I really should add in there the big cloud service providers, Google, Amazon, Microsoft, who are also actively getting into the hardware design business. And the second effect is it's starting to attract venture capital into startups who want to be chiplet vendors. And I think, especially, Bolaji, for you who've been watching the venture capital market for so long, that's got to be fascinating because on the one hand, it looks like it's the next step in fundamental infrastructure for the industry. On the other hand, it's wildly speculative if you're betting on any one company.
Ron, you just put your finger on the question I was going to ask. I'm not sure that I heard any one of our guests talk about the potential size of the market. Did anyone touch on it? And if they didn't, does Ron Wilson have an idea of how big the chiplets market could eventually be?
I have absolutely no idea, but I think if you wanted to estimate it, one way to get a first order estimation would be to extrapolate the size of the entire semiconductor market 5 years or 10 years hence, assuming historic growth, and then take off a chunk of that will always be discrete chips. And there I would look at things like edge computing chips, SoCs, sensor and actuator technology, and purest analog stuff. So I think we could be talking 5 or 10 years from now about chiplet-based multi-die assemblies being the bulk of the revenue in the semiconductor industry, and ordinary SoCs and smaller analog chips and little microcontrollers being the minority.
Yeah. That's something to think about, right?
It's certainly something to chew on, right?
Yeah, but that goes back to the but that predicates, that are we going to have the chiplet open market, right? I mean, it's for SoC to come together where we are today. There's, as Ron mentioned in the very beginning of this discussion, it's like there are IPs people can license and put them together, right? And does chiplet market even get there? I mean, get at when, right?
Mm-hmm. Well, as unfortunately, I think we can all remember, there were people asking exactly that question about the IP market some time ago.
That is so true. In my previous publication that I worked for, we actually had one editor dedicated writing about IP. And I was thinking, like, what IP are they talking about? I couldn't quite understand.
Yes. Well, there was a time when if you wrote a story about IP, you had to specify whether you meant intellectual property or internet protocol.
Wow. There you go.
In that sense, Ron, when you break down the players in the chiplets market, can you break them down?
I think the total supply chain is going to look a great deal like it does today for SoCs. That certainly the EDA industry has to participate. These things are not designable without extensions to today's design flows. The foundries, as you mentioned, but two categories of foundries. Certainly TSMC, Samsung, Intel will be building chiplets because that's the heart of their advanced business. That's where the heart of their advanced business is going anyway. But if the chiplet concept takes off of small, reusable, open dies that can be assembled into systems, that brings in another entire layer of foundries. For instance, it brings in the foundries who haven't stayed on the Moore's Law race. And SMIC, I think, is a perfect case in point. They have had to drop off, not because they wanted to, but because they were forced to. UMC dropped off for financial reasons. Global Foundries dropped off for financial reasons. All those people are suddenly players again, as are some of the smaller foundries who have retreated into specialty processes, but could bring up a viable chiplet process rather quickly. So we have another whole category of players there. In addition to that, you have the assembly and test houses who have to develop new capabilities to make this whole thing work. That's going to be rather expensive, but I think it's going to be very potentially profitable also. So I believe we're going to see more than just the assembly test giants participating in that. And it may very well, unless we all of a sudden become friendly about free trade again, become a regional issue as well as a financial issue.
Yeah.
We may have an assembly and test infrastructure for China, one for India, one for North America, one for Europe, in kind of a worst case scenario.
It's and also like we haven't seen this for a long time, but the foundry business was always owned by foundry business that we know. But a new company like Silicon Box is trying to make its name in Singapore, and I think their customers will kind of bridge both East and West in a way that I think that's where they're looking at their market, right? Sweet spot in a way. Yeah.
Mm-hmm.
Yeah.
Yeah, this technology could be a bridge that is able to cross over the growing trade boundaries that are developing today, because it has the potential to make the pieces from which you assemble a strategically complex and important system in themselves strategically unimportant.
That's actually an interesting point. I hadn't really thought about it, but I think that's actually doable. When we talked to Wayne Dye at Very Silicon, he made a point that Western people tend to think that China is doing chiplets because of export control. And that's part of it, but that's not the primary reason why they want to do it, because they foresee the future where they can buy chiplet or they can design their own chiplet that can actually cross the borders, right?
Mm-hmm.
Yeah.
And I think even if there were no trade restrictions, a lot of the Chinese companies would be interested in chiplets simply because their model has always been to nurture a new technology in a protected domestic market. But that protected domestic market is quite cost sensitive. And chiplets promise, they don't deliver, but today they promise a way to make the entry cost quite low. So you've got much less to recover on the unit price going forward. And if you're trying to grow from a seedling to a tree in a protected domestic market where individuals don't have a lot of spending money, that can be a very valuable thing. So I would think India and China have almost a financial motivation that goes beyond trade barriers.
Yeah.
Ron, the same way you broke down the buckets of players in the market, I'm very interested in how you would categorize the issues, the factors, the challenges, opportunities in the chiplet market. It's a broad question to ask, but you're probably the one that's best placed to answer it. Can we understand what are the factors that you see impacting this market, and how do you see them evolving?
From what we heard from our speakers, I think, again, you have to break the market into today and tomorrow. Today, what Intel and NVIDIA and AMD faced was that they were undertaking something that was physically impossible, and they had to make it possible. So there's been a whole lot of rocket science going on there. And I would hate for people to think that because those three are shipping multi-die assemblies, they did something that was relatively straightforward. They did amazing stuff to make this work at all. Going forward to that third-party open chiplet market, I think we've got a few very fundamental challenges that are still not overcome entirely. One is standards for interconnect between the chiplets. We have UCIe and a few other proposals that define the physical layer, but they don't define enough layers of the protocol stack to guarantee that any two chiplets will be interoperable. Another fundamental problem is the question of getting known good dies to begin with, and then the whole question of testability of not only the individual dies, but the finished multi-die module. those are still unsolved problems, which is probably why you don't see an assembly from Intel with 47 dies on it being shipped in volume today. And then I think there is another issue in that we haven't really settled the substrate question yet. Today, there are basically two choices. If you're rich and doing something really ambitious, you assemble your little dies on a silicon substrate that most people call an interposer because that's what TSMC called it. It's very limited in size. It can be witheringly expensive if it gets close to its maximum size. And it's only available basically through TSMC and Samsung at the moment, although other people are starting to penetrate that market. If you're trying to do something inexpensive, you choose the same organic circuit board substrate that you would use if you were just putting an ordinary die in an ordinary package. That's much less expensive. There are a lot of people who can do it, but it has very severe limitations in terms of how many interconnect lines you can put between two chiplets and how fast you can push signals through those lines. And we're just seeing the leading edge of people trying to make other kinds of substrate technologies viable. We saw a major announcement from Intel mid last year that they've been working with glass, which has its own problems, but promises to have kind of the benefits of both the density and electrical qualities of silicon, but cost closer to that of organic substrates. And we saw a really interesting announcement from Applied Materials just a bit ago, saying that they're looking at extending this notion of novel substrates to kind of merge with the very large panel technology that they've been using for making equipment for producing solar panels. That could potentially not only lower costs a great deal, but could produce large or even huge multi-die assemblies. So I think we have to count substrate technology as a third barrier area.
Okay. No, that's we haven't really touched on substrate. That's a really huge issue. All right. And
no pun intended, I'm sure.
Yeah. But you did mention standardization. That was kind of the questions that I was saving towards the end. We are talking about phi. As you said, there's a layers on top of it. And one of the interesting things that we heard that during the series is that some people are already thinking about domain specific specifications for certain layers. Can you break it down a little bit for us, Ron, on that?
I can't, partly out of ignorance, partly because it may be a little early to have a good taxonomy there.
Yeah.
But just to give an example, if what you're trying to connect together are a giant CPU die and a stack of high bandwidth memory, HBM.
Right.
HBM already defines the bus. And so the only thing you have to worry about is physically, how do I get those electrical signals from one die to the other? And that's pretty much a function of what substrate you're going to use and how far apart are the two things going to be. There are other alternatives besides UCIe and bench of wires, by the way. There's independent companies developing PHYs specifically for multi-die assemblies that are promising better performance, lower power, things like that. But to get back to what I was saying,
yeah,
if you're trying to get between two processing dies, you may want an entirely different protocol at higher layers, something more like PCIe, for instance.
Right.
If you're trying to get between a cluster of processors and a cluster of peripheral controllers or sensor chips, you may want yet a third thing. if you're in a different industry that has different reliability or security requirements, you may have requirements for that interconnect protocol that a graphics processor, for instance, wouldn't have. In autonomous driving, for instance, or certainly in a lot of aerospace applications, you have to think about security. That little interconnect between two dies can't become an attack surface that would allow someone to monitor or interfere with what's going on in the assembly. And that in itself is a profound problem today when it basically imposes encryption on the protocol stack. If anybody ever successfully gets a way to crack our existing security protocols, like quantum computing, for instance, it becomes an even bigger problem because standards for quantum secure encryption haven't emerged yet, and they're almost certainly going to be more complex than what we have today. So, in addition to just different kinds of dies requiring different kinds of high-level protocols, different kinds of systems and different applications may require different kinds of protocols. And so, yes, I think it's almost inevitably going to become protocol or application specific.
Domain specific. Yeah, that's a good point. All right. I'm getting towards the end of my question, which is, I think we covered this, but let's talk about applications for the chiplets. We already know that it is a very, useful thing for people who are making big AI chips or data center, processors. That we know, right? And automotive companies are interested in doing automotive chiplets. What else? I mean, how far can we go? Are we going to have chiplets-based smartphone application processors, or those things are out of question?
I think smartphones are almost low-hanging fruit for chiplets once the supply chain matures a little bit more, because they face the same problem that the industry leaders have faced. They're already building the application processor on as big a die as they can afford.
Sure. Yeah.
Their limitation isn't reticle size. Their limitation is cost and yield, which is related to cost. But if you start saying now, I don't want just a token AI capability in the smartphone that can do some image processing stuff. I want local support for large language modules on my smartphone. That's a huge jump forward, both in memory capacity and in processing power. And the smartphone manufacturers aren't going to get there by just using the next generation to build the same old medium-sized application processor die.
Yeah.
They've got to have a way around. We mentioned aerospace. We mentioned automotive. We should keep an eye on consumer and eventually on edge computing. As the supply chain matures and chiplets become a cost alternative as well as a complexity alternative, those guys are all about cost.
Yeah. All right. That's very good.
Well,
so in order to wrap it up, actually, Bolaji and I talked about this briefly before this session started. We'd like to let our audience know that the Ojo-Yoshida Report is planning the season 2 of this Dig Deeper Chiplet series. And part of the reason is that we'd like to take a broader view of the ecosystem. Ron just mentioned supply chain and also the companies who are in the business of assembly, companies who are making chiplets, the fabs, right? The companies who are actually manufacturing chiplets. And then a whole bunch of startups who are actually getting funded and getting into the chiplet business. I think there's a lot of things to cover for Chiplet 2, but Chiplet Season 2. But I think Bolaji has a couple of related questions on this. Looking forward.
No, not really questions as such. I'm just kind of interested. I'm curious, Ron. You're the host, so what are the areas you would like or that you plan to focus on in Season 2? I'm kind of excited ahead.
Well, I think the The quick response would be all the questions that I dodged in this podcast. But to Junko's point, this is still in the very early stages of being an emerging technology. And by the time we're recording season 2, there will be startups with new ideas, some of which may magically resolve some of the issues we're facing now. There may be people taking this in whole new directions. I think we will start to see traces of other application areas starting to get interested. We're going to start seeing more venture capital flowing into this. And so not only will we have more information about the technologies that we've already talked about, but that aren't settled science yet, we'll also have a lot of industry dynamics to discuss and a lot of new people to talk with.
Right, very good. That's a good wrap. Thank you so much for coming to the show, and please look forward to the season 2. Thanks. Bye.
Chiplet-based multi-die systems are taking the industry by storm. Are you ready for new and unfamiliar challenges around die-to-die connectivity, chiplet integration, and system reliability? Synopsys, backed by its broad experience, close ecosystem collaborations, and comprehensive IP and EDA solution, offers help for fast chiplet-based multi-die system development. Visit synopsys.com/multi-die